Like we considered the performance of a router at the input port, let's also see what happens when a router outputs the packets. Is it always a perfect systematic situation, or anomalies could happen? Well, we'll see that buffering could take place at the output port, and because of that, the output port could also overflow. Then we'd also look at how much buffering could be done and what are the recommended guidelines for hardware manufacturers and vendors. When a router has finally given an incoming packet and output port, the packet is supposed to pass through the switching fabric and land into the output port. It may be possible that buffering is required when datagrams arrive from the switching fabric faster than what the other network can handle. This could be a scenario where we are connecting two different networks. The input network is high speed, the router is also high speed, but the output network is slower. This could be once we are sending traffic from Ethernet network to point serial line network. Since the data rates are different, so this buffering is going to happen at the output port. As an instance, if our switch is n times faster than our line, that is, the switching rate at the switch is n times faster than that of line, then buffering is bound to happen. The buffering could also become in surplus or excess if the scheduling discipline is not appropriately chosen. We'll talk about different queuing and scheduling disciplines which affect the input and output buffering which is performed at the router. Illustratively, router output interface provides buffering as one of the most important features because whatever datagrams are being sent out of the router have to be buffered in first before they are sent down to the network interface card or the serial interface. The output port buffering could be visually understood through this scenario. Here we see on the left hand side we have at time t packets are coming from input to output ports very fast because the packets are already there in the input ports. The switching fabric is also fast. So here we can see that after one packet time, the switching fabric has already outputted two red packets in the top right output buffer. Now, in place of one, two packets have been placed in the output, so these have to be buffered anyways. This is where the output buffering comes into play. The hardware manufacturers and network vendors have to take into consideration how much buffering is required at the output port is actually determined through RFC 3439 that gives insight into the buffering requirements on the basis of the round trip time and the link capacity. For instance, if the round trip time is 250 milliseconds and the link capacity is 10 gigabits per second, this is a scenario where we have high bandwidth delay product because we have very large channel capacity and the round trip time is also large. So we need 2.5 gigabits worth of buffer size. This is a good approximation to the requirements for a router, which is placed at the core of a network. If we have multiple flows where each flow is coming from an individual source and going to a unique destination represented by n, for n flows, the buffering requirement is actually reduced. Why is that? Because at an individual level, each buffer is going to be handled and in a way congestion managed by the individual TCP management at individual flows. So for n flows, the buffering requirement is round trip time times the channel capacity divided by square root of the number of flows.